Today we discuss on linearization technique of two species model and stability analysis. Today we discuss on two-dimensional nonlinear system for two species, and first we define equilibrium points of this nonlinear system. Then we discuss linearization technique for this system, and next we discuss the stability of the equilibrium points in the different cases. First, to define what is the two-dimensional nonlinear system. Here, consider a population of two interacting species with population densities xt and yt. We consider two interacting species with densities xt and yt. Assume that xt and yt are both continuously differentiable function of time t. The model equation for the interacting nonlinear system be of the form dxdt equals to f of xy and dy/dt equal to g of xy. This is the general form of two-dimensional nonlinear system because of the term right hand side function fxy and gxy are in general nonlinear term, and so this system is nonlinear system, first order differential equation. Now the equilibrium points or steady states of this system 1 is the point, equilibrium point x star y star. X star y star, I call it equilibrium point for dx dt equal to 0 and dy dt equal to 0. So dx dt equal to 0 means there is no change in x with time t, and also there is no change in y with time t at those points x star y star. X star y star are these types of points where dx dt equals to 0 and dy dt equal to 0 simultaneously. And so we can say for this equilibrium point or steady states x star y star, the function f x star y star equal to 0 and also g of x star y star is also 0. So equilibrium points, we can find equilibrium point by solving the system 2, and so we can say f x star y star equal to 0 equals to g x star y star. Thus an equilibrium point x star y star is a constant solution of the system 1, two-dimensional nonlinear system 1, and xy do not change with time t at the point x star y star. So x star y star is a particular point in the phase space where dx dt equal to 0 as well as dy dt equal to 0. No change in x and y with time t. Now we discuss the linearization technique. Linearization, because of the nonlinear term function fxy and gxy in the system 1, it is too much difficult to solve the system. So we first linearize the system. Linearize in terms of x and y, because here x and y are unknown variables. Linearization result can only give information about the behavior of the solutions near the equilibrium. Linearization only give us the information about the equilibrium point. They will not enable us to examine such questions as the existence of periodic orbits, whether there exist of periodic orbits for the solution. The linearization is an important tool in population dynamics for the study of local behaviors about the equilibrium. So, for this, we introduce two variables u and v, such that u equal to x minus x star and v equals to y minus y star. Here x star y star equilibrium point is an equilibrium point, and x and y are densities of the two species respectively, and u is new variable and v is also new variable, such that x minus x star and v equals to y minus y star. Here x star and y star is constant, but x and y are variable with time t. Now by this equations in 4, transform the system 1. So the equation system we have the system 1 is such that system 1 dx dt equals to f of xy, and we have the new variable u equals to x minus x star and v equals to y minus y star. So this v equals to y minus y star. So x here dx dt. So from this we get du dt equals to dx dt minus dx star dt, but x star is constant, so this term equals to 0. So du dt equal to dx dt. So we can transform this first equation of the system 1 dx dt by du dt. So dx dt equal to, we can write du dt, and this f of x, in place of x we write u plus x star, because from this x equals to u plus x star, so we write u plus x star, comma, and from the second variable v, y equal to v plus y star, so v plus y star. So the equation dx dt equal to fxy transform as du dt equal to f of u plus x star comma v plus y star in terms of ut. And similarly, other second equation of the system 1 dy dt equal to g of xy can be transformed in the new variable uv. This equals to, similar way, dv dt equal to g of u plus x star comma v plus y star. So in terms of in terms of new variable, we can change, we can transform the system 1 as du dt equal to f of u plus x star and comma v plus y star, and dv dt equal to g of u plus x star comma v plus y star. Now by Taylor's series expansion of the function f for xy near the equilibrium point x star y star, we get f of xy equals to f of x star y star plus f of x means del f del x at x star y star into x minus x star plus del f del y x star y star at the point x star y star into y minus y star, and plus second partial derivative, second order partial derivative del 2f del x square by 2 at the point x star y star x minus x star whole square plus f of xy at the point x star y star x minus x star into y minus y star, and plus f yy by 2 at the point x star y star into y minus y star whole square plus dot 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 dot. So this is the Taylor series expansion for two-dimensional variable fxy. So using this Taylor's series expansion for two-dimensional variable, we can expand the right hand side of the system phi. So the first equation in the phi, this expression right hand side expression in the equation 5, first equation of 5, f of u plus x star comma v plus y star. So using this Taylor expansion, we can write this x means u plus x star, because we have the variable x u equals to x plus x minus x star and v equal to y minus y star. So x equal to u plus x star, so put here u plus x star, and y equal to v plus y star, so put here v plus y star, and f x star y star and del f del x, that is fx x star y star, and x minus x star equal to u by this u, so put here into u, and f of f y del f del y at the point x star y star, y minus y star means v, and this function second order partial derivatives, collection of all second order partial derivatives, this by h1 uv. We introduce here new function h1, which is a function of u and v, because this x minus x star is u and y minus y star is v. So this is a function of h1 uv. This h1 uv is a function that is small for small deviation, that is perturbation. This perturbation term is u and v. uv are perturbation term near the equilibrium point x star y star. So we choose as this perturbation, small perturbation, due to small perturbation, this second order derivative h1 uv by root over u square plus v square, this limit double limit uv tends to 0 0, obviously 0, and hence these second order partial derivatives are all 0. So we collect only here the up to the first order partial derivative, collect the terms of the first up to first order partial derivative. And also note that then since x star y star is an equilibrium point, so f of x star y star equal to 0, because already we have defined this equilibrium definition of equilibrium points, f x star y star equal to 0 and g x star y star equal to 0. So this first term f x star y star is also 0, and due to small perturbation, this h1 uv is also by root over of this also 0, tends to 0. So f u plus x star comma v plus y star equal to fx x star u star into u, f y x star y star into v. So we get this from this expression is f of u plus x star comma y plus v plus v plus y star. This is wrong. This is y star. So v plus y star equal to equal to equal to f of x at the point x star y star into u plus f of y at the point x star y star into p. Similarly, we can get from the function g. So g u plus x star comma v plus y star is also g of x star y star plus gx into u, but this g x star y star is also 0. So this term equals to 0. So we get this equals to this. So from the system 5, we can write du dt equal to u del f del x at x star y star plus v del f del y x star y star. And from second equation of 5, dv dt equal to g of u plus x star comma v plus y star. So we get dv dt equal to u into g del g del x x star y star plus v into del g del y x star y star. They call it equation 6. And this system is a linear system of the given nonlinear system 1. Now we can solve this linear system 6. So this is the technique of linearization about the equilibrium point of the nonlinear system 1. And because this system is linear system, because here the unknown variable is u and v. So here power of u is 1 and power of v is 1, power of u is 1, power of v is 1. So this system is a linear system in u and v. So we can easily solve it. But later we discuss that we not solve analytically, but we draw the phase portrait, the nature of the solution, to find the nature of the solution. Now we can write the system 6 in the matrix form. Du dt matrix, column matrix du dt dv dt equal to the coefficient matrix f x comma y x star comma y star, f y x star y star, gx x star y star, gy x star y star, coefficient matrix, and this into the column matrix u and v. This 7. This coefficient matrix, call it capital J. This fx fy, that means del f del x del f del y, in second row del g del x del g del y at the point x star y star. This matrix is called community matrix or Jacobian matrix or variational matrix of the system 1, nonlinear system. So this is the community matrix or Jacobian matrix of the given nonlinear system 1, and corresponding equation system 6 is called the linearization system, linear system of the given system 1. It describes the effect of size of each species on the growth rates of itself and the other species at equilibrium. It describes means this system 6 describes the effect of size of each species. Each species means corresponding to x species, corresponding to y species, on growth rates. On growth rates means because of du dt and dv dt is the growth rate, and because du dt is the this is the du dt equals to dx dt and dv dt equals to dy dt. So this gives the growth rates of itself and the other species at equilibrium point, because we determine this Jacobian at the point x star y star. So at the point x star y star equilibrium point, we get the corresponding growth rate of this species and the other species at equilibrium point. Now we discuss the stability of the equilibrium point. The equilibrium point x star y star is said to be stable if every solution xt yt with initial condition x0 y0 at time t equal to 0 sufficiently close to the equilibrium, remains close to the equilibrium for all t greater than 0. For all time t, this equilibrium point is called stable if every solution x t y t with initial condition x0 y0 sufficiently close to the equilibrium point remains close to the equilibrium for all t greater than 0. And asymptotically stable means an equilibrium point x star y star is said to be asymptotically stable if it is stable. Stable means this is the first definition, stable, and if in addition the solution x t y t tends to the equilibrium point x star y star as t tends to infinity. So this is the stable and asymptotically stable means that suppose this is the point x star y star, this is the equilibrium point in the phase space. Now this is the solution trajectory. This trajectory some closed orbit in this near about the point near equilibrium point, this some trajectory goes to the neighborhood of x star y star for all time t greater than 0. Time t greater than 0. This solution trajectory, this x-axis, this y-axis, x-axis, y-axis, this solution trajectory close to the equilibrium point, close to the equilibrium point. This is the stable. So then we say this equilibrium point is stable. But asymptotically stable means this x star y star is stable equilibrium point, and all solutions goes to the point x star y star at time t tends to infinity. At time t tends to infinity, the solution trajectory with some initial condition. Suppose this is the initial condition. Suppose starts from here. So this x0 and y0. Suppose at time t equal to 0. So then this trajectory goes to the equilibrium point in the phase space x and y. So this is called asymptotically stable. Asymptotically stable. And first, this solution close to the equilibrium point is called only stable. So asymptotically stable means it is stable as well as it goes to the point x star y star as t tends to infinity, time tends to infinity. So this is the asymptotically stable. Next, we show the criteria for the stability of this equilibrium point. Now, we find the characteristic equation of the system 6. System 6 is this linear system corresponding to the nonlinear system 1. So, for this system, this is the linear system. For this system, we get the characteristic equation by the a11 minus lambda, a12, a21, a22 minus lambda. Here a11 means this is the coefficient matrix fx, and a12 means fy, and a21 means gx, and a22 means gy at the point x star y star. So this is the notation all defined here. This later on we define this at the point this a11 fx, a12 fy, a21 gx, a22 gy at the point x star y star. And so the characteristic equation of the system 6 is given by this, and after simplification we get a word equation in lambda, this lambda square minus a11 plus a22 into lambda plus a11 a22 minus a12 into a21 equals to 0. And this a11 plus a22 is called T. This is the trace of the Jacobian matrix G, and this A11 A22 minus A12 into A21 is the determinant of the Jacobian matrix G. So we notation here, we give the notation here. T means for trace of J, that is the sum of the diagonal elements A11 A1 A1 A12, and delta is the determinant of the Jacobian J, A12 into A22, A11 into A22 minus A12 into A21. Now the discriminant for this equation 9 is the b square minus 4ac. So here b square is t, so minus t square minus 4a, a means 1, and delta c delta, so t square minus 4 delta. So by this discriminant we can get the two roots of the equation 9, and these two roots are called the eigenvalues of the system 6 of the matrix of the Jacobian of G matrix, Jacobian matrix G. So eigenvalues are the lambda 1 equal to minus b plus minus root over b square minus 4ac by 2 by Trajectory formula, and lambda 2 equal to t minus root over d by 2. These are the two eigenvalues. So nature of these two eigenvalues depend on the nature of the discriminant t square minus 4 delta. If t square minus 4 delta d is greater than 0, then we get two real and distinct eigenvalues. If d equal to 0, we get two equal eigenvalues, there's double root t by 2, and if d discriminant is negative, then we get two complex eigenvalues. So now we only give the statement of the theorem. The equilibrium point x star y star is asymptotically stable if the roots of the characteristic equation 9, this is the lambda square minus t lambda plus delta equal to 0, this is called characteristic equation of 9, have the negative real parts. By Routh-Hurwitz criteria, the necessary and sufficient condition for the eigenvalues lambda to have the negative real parts and are t less than 0 and d delta greater than 0. So we will discuss on the Routh-Hurwitz criteria in the later class, next class. Routh-Hurwitz criteria. This is the criteria for the negative real part eigenvalues, for the eigenvalues to have the negative real part for asymptotically stable. For asymptotically stable, Routh-Hurwitz gives the statement that for this equation 9, this trace must be negative and determinant value must be positive. Then we can say this equilibrium point is asymptotically stable. Now these eigenvalues, two eigenvalues lambda 1 lambda 2 are real and negative, then equilibrium is an asymptotically stable node, asymptotically stable node. Because when these lambda 1 lambda 2 are negative, then the solution term x and y, we get x equal to some e to the power minus lambda this lambda 1 into t and plus some constant into lambda 2 t. So when lambda 1 negative, then this tends to 0. This tends to 0. Some constant this tends to 0. This term tends to 0 as lambda 1 negative, t tends to infinity. So these are asymptotically stable when both the eigenvalues are negative. This is the condition. So you have to check the eigenvalues. We have to check the eigenvalues whether they are real negative or real positive or one negative, one positive, and complex, and so on, so on, so on. So when you get two eigenvalues lambda 1, lambda 2 real and negative, then equilibrium point x star y star is an asymptotically stable node. If lambda 1, lambda 2 are real and positive, lambda 1, lambda 2 real and negative means lambda 1 is less than lambda 2 is less than 0, or lambda 2 less than lambda 1 less than 0. So then we can say this x star y star equilibrium point x star y star is asymptotically stable. So x star y star is stable and tends to xy tends to x star y star as t tends to infinity. And when lambda 1 lambda 2 real and positive, and suppose lambda 1 greater than lambda 2 greater than 0, both are positive, or lambda 2 greater than lambda 1 greater than 0. So here lambda 1 must be according to a choice. This lambda 1 must be greater than lambda 2. Lambda 1 is greater than lambda 2 because this minus sign. So lambda 1 greater than lambda 2. So this equilibrium is an unstable node. Lambda 1 lambda 2 when both are positive, because due to term e to the power lambda 1 t and some constant of e to the power lambda 2 t, when t tends to infinity, this e tends to e to the power lambda t tends to infinity. So this unstable node. And third case, when eigenvalues are real and opposite signs. Suppose lambda 2 less than 0 less than lambda 1. So lambda 1 positive, lambda 2 negative. So we can say this is the saddle point. Some is stable, some is unstable. Some part of the trajectory is stable and some part of the trajectory is unstable. So when they are of opposite sign, so we get a saddle point. And number case 4, when lambda 1 lambda 2 complex with negative real parts. Suppose lambda 1 lambda 2 equals to alpha plus minus I beta, and real parts means alpha. And alpha, if alpha is negative, then we can say this equilibrium point x star y star is stable focus. And case 5, if alpha 1 alpha 2 complex with positive real part, and when this alpha plus minus I beta complex root and real part is positive, so alpha is greater than 0, then we can say equilibrium point x star y star is unstable focus. Here stable focus, here unstable focus, when the positive real part exists in the complex root. And last case 6, if lambda 1 lambda 2 are purely imaginary, so here alpha equals to 0, so real part equal to 0, then the linearized system we have the center means this is the elliptical way or circular way, this path is center. But the original nonlinear system will have a center or stable or unstable focus depending on the nonlinear terms. So for particular problem, then we get the particular case. Now for this we draw a graph along the x-axis, horizontal axis, this is delta, this is determinant j, and along the vertical axis we get the trace t, and this is the curve, dotted curve is the parabolic curve, is t square minus delta. So t square minus delta means d. So this curve represents d equal to 0. The variable, this variable is t variable, vertical variable, and horizontal variable delta variable. So this curve is the t square minus 4 delta equal to 0, that is d equal to 0. So this is the represents, this parabolic path represents the curve t equal to 0. When for particular system you get for this point, this in this region, so we get here this region, this region, this region, this region, this region, this region, this region. So this for this parabolic path, this upper part is the region is d greater than 0, and on the parabolic path d equal to 0, discriminant equal to 0, and this inner part is called the d less than 0. So we get 3 space in this t delta space. So upper part is d greater than 0, so these are all d greater than 0, this portion is all d greater than 0, and this inner side portion all d is negative, and on the parabolic path d equal to 0. When for a particular Jacobian matrix, when we get for the Jacobian matrix, we can find t and delta for the particular Jacobian matrix. So calculate t and delta. Suppose for t equal to, suppose t equal to, say you get suppose 4 and delta equal to get 5. So then for the particular Jacobian, we suppose you get t equal to 4, delta equal to 5, then the point belongs to this, suppose this here. So then from this you get this unstable node. And for this different region, when t delta belongs to this region, this is the unstable focus. When t delta lying on this delta axis, then the center and this portion saddle point, and this stable focus, and so on. Now we can draw a schematic diagram for when d equal to t square minus 4 delta discriminant for this system, for this equation lambda square minus t lambda plus delta equal to 0 characteristic equation. When d greater than 0, that means real and distinct eigenvalues, and lambda 1 lambda 2 not equal and real. Then we get three cases, when t less than 0 and delta greater than 0, t greater than 0, delta greater than 0, and delta is less than 0. When t less than 0, delta greater than 0, we get stable node, and for this case lambda 2 less than lambda 1 less than 0. Both are negative, eigenvalues are both are negative, then we can say this is stable node. And when lambda 1 greater than lambda 2, lambda greater than 0, then unstable node. In this case, t greater than 0, delta greater than 0. And when one positive, one negative, so lambda 1 less than 0, lambda 2 greater than 0, then we then get delta negative, and this is the saddle point. And then in this region belongs to this delta less than 0, so this is the saddle point. And when d equal to 0, then the real and equal roots lambda, so lambda 0, suppose call it lambda 0 and lambda 0, this is the double real root, then degenerate solution. And for this there are two cases, lambda 0 less than 0, and lambda 0 greater than 0. For first case, the stable node. When lambda 0 greater than 0, the unstable degenerate node. And third case, when d is negative, there is complex roots with eigenvalues alpha plus minus I beta. Then also we get three cases, this alpha equal to 0, then t equal to 0, purely imaginary eigenvalues. We get center, equilibrium point is center, and when t greater than 0, that is positive real part of the complex root alpha greater than 0, so we get unstable focus. And when t negative, that is complex root of the real part is negative, then stable focus. And this is the case. Now we draw the different cases in this diagram. Here this is the trace along the horizontal axis, and here determinant is vertical axis. In our note, in the horizontal axis determinant and vertical axis is trace. So parabola is this in this way, and in our note this is the we draw in this way. Now suppose eigenvalue. So first both eigenvalues are real and distinct. Then this case, when both eigenvalues are real and distinct, this lambda 1 lambda 2 gives the eigenvalue. Suppose here lambda so here when trace is here, trace is positive, and determinant is also positive, delta is also positive, then we get here two eigenvalues, lambda 1 lambda 2, both are positive, and for this case, when both are positive, both are negative, both are negative. In this region, when trace is negative and delta is positive, belongs to this region, this plus sign, and then notice that here lambda 1 equal to negative and lambda 2 negative. So lambda 1 negative, lambda 2 negative. So in this case, we get the trajectories in this way. These are the trajectories. So you can draw by clicking anyways. These trajectories. Notice that this arrow going to the origin here. 0, 0 is the equilibrium point here. So this trajectory goes to the equilibrium point 0, 0 here with time t tends to infinity, and all trajectories goes to equilibrium point. All trajectories goes to infinity when lambda 1 negative, lambda 2 negative. Then this equilibrium point here 0, 0, here 0, 0. So here is the stable node. Is the stable node. It's called stable node. All trajectory goes to the equilibrium point when both eigenvalues are negative. And second case, real and positive. Eigenvalue both are real and positive. Real and positive. Here in this region plus sign is here. So trace here, trace is positive and delta is also positive. Trace is also positive, delta is also positive. So in this case, so notice that these trajectories goes away from the equilibrium point. All trajectories goes away from the equilibrium point, and here eigenvalues lambda 1 is positive, lambda 2 is positive, and trajectories are all away from the equilibrium point. So this is the unstable node. Unstable node is actually called nodal source. Nodal source. Nodal source. And third case, when lambda 1, lambda 2 real and opposite sign. When lambda 1, lambda 2 real and opposite sign. Suppose yes here. So plus sign is here. So here means at this point. So trace is positive and delta is negative. Delta is here. So trace delta is here. Delta is negative and trace is positive in this region. Then eigenvalues, notice that eigenvalues lambda 1 is negative and lambda 2 is positive. So one eigenvalue negative, one eigenvalue positive in the third case. So when negative along the path, negative path, the trajectories goes to equilibrium point, and along the due to the presence of the positive eigenvalue, so along these trajectories, for these trajectories, this trajectory goes to away from equilibrium point with time. So here notice that this is the equilibrium point is here origin. Suppose this trajectory is this point is away from origin. This away from origin, and this trajectories away from origin. This trajectories goes to equilibrium point and then go to infinity or away from origin. So this equilibrium point is called saddle point. This equilibrium point is called saddle point. And fourth case, lambda and lambda 2 complex with negative real part. Complex and negative real part. This complex with positive, this complex and negative real part. This here plus and is here. So here trace is negative and determinant is positive. Determinant value is positive. Jacobian determinant of the Jacobian is positive. So notice that eigenvalues lambda and lambda 2 are complex values, and here both real part are negative. So alpha here negative, and alpha in lambda 2 alpha here also negative. So when this negative and this is the stable focus, so all trajectories goes to the equilibrium point, with time increases. So this is called stable focus, and in alternatively called spiral sink. So suppose here is x0 y0 is the initial value of the x and y, and for this x0 y0 this trajectory goes to the equilibrium point along this trajectory. If you choose x0 y0 x0 y0 is here, notice that these x and y are all in the first quadrant because it is a population dynamics. So xy cannot be negative. So start from this x and y are both positive. Then this x0 y0 at time t equal to 0. So this x0 y0 is here. Then this path is going to the equilibrium point along this trajectory with time t, and alpha is negative, and here lambda 2 in the eigenvalue complex eigenvalues, real part is negative, real part is. And fifth case, complex eigenvalues and positive real part is here. So in this case, trace is positive, determinant is positive, and trace is also positive. And notice that here first eigenvalue is complex and second eigenvalue also complex, and both the real part are positive. Both real are positive. So then we get the trajectory is away from origin, or away from equilibrium point. So this is called unstable focus. When the both real part of the complex eigenvalues are positive, then this unstable focus actually it is also called spiral source or spiral source. And last case, when this is the purely imaginary, both eigenvalues are purely imaginary. So purely imaginary, in this case, purely imaginary, the center determinant is this purely imaginary, this point here. When point lies is here, so on this point, trace is 0 and determinant value is positive, and the eigenvalues lambda 1 is purely imaginary and lambda 2 is also purely imaginary. There is no real part. So when purely imaginary, so you get this center means this equilibrium point, we get elliptical path on this. So with time t, suppose this is the x0 y0, this point is x0 y0, then if you start from this point, initial point x0 y0, then x and y goes to this path with time increased time t, and all time t. This is called center. This is the sixth case and last case, and this is the discuss with the stability of the equilibrium points or steady states. Hello, Somallo, Himatri, Vedobrato, Odris.
Yes, sir.
Yeah, sir.
Do you follow today's class?
Yes, sir.
Okay, thank you. I stop today's lecture.